Let's talk about space-time. It sounds like something from a science fiction movie. And it kind of is, but it's also real. It's the world we live in. To get what it is, we have to go back and undo some things we think we know about space and time. We usually think of space and time as two different things. Space is the big empty box that everything is inside. It has three dimensions: up and down, left and right, forward and back. You can move around in it. You can point to a location in space. It's the stage. Time is different. Time is like a river. It just flows. It always moves forward, from the past through the present into the future. We can't stop it or turn around in it. We're all just carried along for the ride. It's the universal clock that ticks the same for everyone, everywhere. That was the old way of thinking. It's how Isaac Newton saw the universe. He gave us laws of gravity and motion that worked incredibly well. We use them to predict the paths of planets. We still use them to send rockets to the moon. This view of a separate space and a separate absolute time feels right. It matches our everyday experience. But at the end of the 1800s, scientists started noticing a crack in this idea. The problem was light. A scientist named James Clerk Maxwell came up with a set of equations that described electricity and magnetism. His math predicted that light was an electromagnetic wave, and it predicted that this wave should always travel at a specific speed. A very, very fast speed, about 671 million miles per hour. The weird part was that the math said this speed was always the same. It didn't matter if you were moving toward the light or away from it. The speed of light was constant. This broke Newton's rules. Think about it. If you're on a train moving at 50 miles per hour and you throw a ball forward at 20 miles per hour, someone standing on the ground sees the ball moving at 70 miles per hour. Speeds add up. That's common sense. But light didn't work like that. If you're on a spaceship moving at half the speed of light and you turn on a flashlight, the light from that flashlight still moves away from you at the full speed of light. And someone watching you from a planet would also see that same beam of light moving at the exact same speed. Not 1.5 times the speed of light, just the speed of light. This was a huge puzzle. How could the speed of light be the same for everyone, no matter how they were moving? It didn't make sense. Something had to be wrong. Either Maxwell's equations were wrong, or our basic understanding of space and time was wrong. This is where a young patent clerk named Albert Einstein came in. Einstein decided to take Maxwell's equations seriously. He started with two simple ideas. First, the laws of physics should be the same for everyone who is not accelerating. Second, the speed of light is the same for everyone. He took these two ideas and followed them to their logical conclusion. And that conclusion changed everything. Einstein realized that for the speed of light to be constant for everyone, space and time themselves must not be constant. They must be flexible, they must be able to stretch and shrink depending on how you are moving. He saw that space and time are not two separate things. They are woven together into a single, four-dimensional fabric. He called it space-time. This is the big idea. It's not a three-dimensional world that changes over time. It's a four-dimensional world called space-time. 3 dimensions are space, and the fourth dimension is time. You can't have one without the other. They are part of the same thing. Think of it like this. To describe an event, you need 4 pieces of information. You need to say where it happened in space, its coordinates, like latitude, longitude, and altitude. And you need to say when it happened in time. For example, I met my friend at the corner of 5th and Main on the 10th floor at 3 p.m. That's a location in space-time. Everything you do, every moment of your life, is a journey through this 4-dimensional space-time. Even when you're sitting perfectly still, you are still moving. You're moving through time. You're traveling into the future at a rate of 1 second per second. Einstein's new idea, called special relativity, had some very strange consequences. One is that time can slow down. If you start moving very fast through space, you start moving slower through time. This isn't a feeling. It's real. If you flew in a spaceship at near the speed of light for a year, you would age 1 year. But when you came back to Earth, you would find that many, many years had passed. Your friends and family would be old, or maybe even gone. You traded your motion through time for motion through space. This is called time dilation. It's been measured. Clocks on fast-moving GPS satellites tick just a tiny bit slower than clocks on the ground. It's a small effect, but if we didn't account for it, your GPS would be off by miles every single day. Another consequence is that space can contract. If you're moving very fast, the distance to your destination actually gets shorter from your point of view. An object moving at high speed will appear squished in the direction of its motion. This is called length contraction. So space and time are relative. My experience of space and time might be different from your experience of space and time if we are moving differently. But we can both agree on one thing, the speed of light, and we both exist in the same underlying reality, space-time. This was a revolutionary idea. It replaced Newton's static stage with a dynamic, interconnected fabric. But Einstein wasn't done. His theory of special relativity was great, but it was missing something big. It didn't include gravity, it only worked for things moving at a constant speed, not for things that were accelerating. Einstein spent the next 10 years working on this problem. He wanted to fit gravity into his new picture of the universe. He had what he called his happiest thought. He was sitting in his chair at the patent office and imagined a person falling from the roof of a building. He realized that as the person was falling, they would not feel their own weight. They would feel weightless. If they took a coin out of their pocket and let it go, it would just float there next to them. In that moment, for that falling person, gravity would seem to have disappeared. Then he imagined a person in a closed elevator in deep space, far from any gravity. If a rocket on the bottom of the elevator started firing, pushing the elevator up, the person inside would feel a force pushing them to the floor. If they dropped a coin, it would fall to the floor. They would feel weight. They would have no way of knowing if they were sitting on Earth, feeling gravity, or accelerating in space. This was the key insight. The effects of gravity are exactly the same as the effects of acceleration. He called this the equivalence principle. This connected his old theory to his new problem. If acceleration could affect space-time, which he already knew from special relativity, and if gravity was the same as acceleration, then gravity must also affect space-time. And this led to his masterpiece, the general theory of relativity. Here is the central idea of general relativity. Gravity is not a force. We think of gravity as a force that pulls things. Newton said the sun pulls on the Earth, keeping it in orbit. But Einstein said that's not what's happening. Einstein said that mass and energy bend space-time. They create curves and dips in the fabric of space-time, and what we feel as gravity is just us moving through that curved space-time. The classic analogy is a bowling ball on a trampoline. Imagine a big, flat, stretched-out rubber sheet. That's flat space-time. If you place a heavy bowling ball in the middle of it, the sheet will sag. It will curve. Now, if you roll a small marble nearby, the marble won't travel in a straight line. It will follow the curve in the sheet created by the bowling ball. It will start to circle the bowling ball. From the marble's point of view, it is going in a straight line, but the space it's moving through is curved. To an outside observer, it looks like the bowling ball is pulling the marble, but there is no invisible rope. There is no force. There is only the shape of the rubber sheet. That's what gravity is. The sun is a massive object. It creates a huge dip in the fabric of space-time around it. The Earth, like the marble, is just moving in what it thinks is a straight line through this curved space-time. But that straight line in curved space-time is a circle, an orbit. The Earth is basically free falling around the sun. This is a mind-bending idea. Matter tells space-time how to curve, and the curve of space-time tells matter how to move. It's a beautiful interconnected dance. So, can we bend space-time? The answer is yes. We are doing it right now. You are bending space-time. Your body has mass. It creates a tiny, tiny little dent in the fabric of space-time. The Earth is bending space-time. That's why if you drop your phone, it falls to the ground. It's not being pulled by a force. It's following the curve in space-time created by the Earth's mass. The phone is just taking the straightest possible path through a curved world. Every object with mass or energy bends space-time. The more mass, the more it bends. A planet creates a bigger bend than a person. A star creates a bigger bend than a planet. A black hole is an object so dense that it bends space-time into an infinitely deep well, a point of no return where the curvature is so extreme that not even light can escape. So yes, space-time can be bent, and it is being bent all around us all the time. But the next question is, can we bend it on purpose? Can we control it? This is where we move from established science into the realm of theoretical physics and science fiction. The answer is maybe, but it would take an amount of energy that is almost impossible to imagine. To create a noticeable warp in space-time, you need an incredible concentration of mass or energy. The kind of bending we do just by existing is microscopic. To do something useful, like travel faster than light, you need to manipulate space-time in a very dramatic way. One idea for this is the Alcubierre drive, more commonly known as a warp drive. The idea was proposed by a physicist named Miguel Alcubierre in 1994. He realized that Einstein's equations allowed for a very strange solution. A warp drive wouldn't work by moving a ship through space really fast. The laws of physics say that nothing with mass can travel at the speed of light, let alone faster. A warp drive gets around this problem. It doesn't move the ship through space, it moves space itself around the ship. Imagine a bubble of space-time around a spaceship. The Alcubierre drive would work by compressing space-time in front of the bubble and expanding space-time behind it. The ship inside the bubble would stay perfectly still. It wouldn't be accelerating or moving at all. It would be in its own little pocket of flat space-time. But the bubble itself, carried on this wave of expanding and contracting space, could travel at a speed faster than light. It's like you're on a surfboard. You aren't moving on the board, but the wave is carrying you and the board to the shore very quickly. The ship is the surfer, and space-time is the wave. It sounds amazing, and mathematically, it works. It doesn't violate general relativity, but there's a huge catch. To make it work, you would need something called exotic matter. This is matter with negative mass or negative energy density. We don't know if this kind of matter exists. All the matter we've ever seen or created has positive mass. It bends space-time down, like a bowling ball. Negative mass would have to bend space-time up, creating an anti-gravity effect. It would push things away instead of pulling them in. And you would need a lot of it. The initial calculations suggested you'd need a ball of exotic matter with the mass of the entire planet Jupiter. More recent calculations have brought that number down, but the energy requirements are still astronomical, far beyond anything we could ever hope to produce. So, while a warp drive is theoretically possible according to the math, it's not something we can build with any technology we can even imagine today. Another way to bend spacetime for travel is a wormhole. This is another idea that comes directly out of Einstein's equations. A wormhole, also called an Einstein-Rosen bridge, is a shortcut through spacetime. Imagine spacetime is a giant sheet of paper. To get from one point on the paper to another, you have to travel across the surface. But what if you could bend the paper, folding it over so the 2 points are right next to each other? Then you could just poke a hole through the paper and go straight from one point to the other. That hole's a wormhole. It would be a tunnel connecting two very distant parts of the universe. You could step through a wormhole in your living room and end up in another galaxy moments later without traveling through all the space in between. Like the warp drive, wormholes are allowed by the math of general relativity, but they also come with major problems. First, they are thought to be incredibly unstable. The moment you tried to go through one, it would collapse into a black hole. To keep a wormhole open, you would again need a huge amount of that same exotic matter with negative energy. You'd have to use it to line the throat of the wormhole to prop it open and stop it from collapsing. Again, we don't know if this stuff exists or if we could ever create it, so wormholes remain firmly in the realm of theory. These futuristic ideas show that the concept of bending space-time is a serious one in physics. It's not just a weird side effect of gravity. It is the very nature of gravity, and understanding it has led to very real practical results. We need to know that space-time is bent to make our GPS work. We've also seen proof of it in spectacular ways. One of the first proofs of general relativity came in 1919. Einstein's theory predicted that the massive sun should bend the space-time around it. This means that light from distant stars passing near the sun should also follow this curve. The path of the light should be bent. During a solar eclipse, when the sun's light is blocked by the moon, we can see the stars that are right next to the sun in the sky. An astronomer named Arthur Eddington led an expedition to observe an eclipse. He took photographs of the stars near the sun. He then compared these two photographs of the same stars taken at a different time of year when the sun was in a different part of the sky. He found that the positions of the stars in the eclipse photos were slightly shifted. The light from the stars had been bent as it passed the sun, exactly as Einstein had predicted. It was a huge confirmation of his theory. The news made Einstein a global celebrity overnight. Space itself was not a fixed straight grid. It could be warped. Another piece of evidence is called gravitational lensing. When light from a very distant galaxy passes a closer, massive galaxy on its way to us, the space-time around the closer galaxy acts like a lens. It bends the light, sometimes creating multiple images of the distant galaxy or smearing its image into a ring or an arc. We've taken amazing photos of this effect with the Hubble and James Webb Space Telescopes. We are literally seeing space-time being bent by the gravity of a galaxy, but perhaps the most incredible proof came just a few years ago. Einstein's theory predicted that when very massive objects like two black holes or two neutron stars spiral into each other and merge, they should create ripples in the fabric of space-time itself. These ripples, called gravitational waves, would travel outward at the speed of light, stretching and squeezing space as they go. For decades, scientists thought these waves would be too small to ever detect, but in 2015, an incredible experiment called LIGO, the Laser Interferometer Gravitational Wave Observatory, did it. They detected a tiny ripple in spacetime that had traveled for over a billion years to reach Earth. The ripple was created by the collision of two massive black holes. LIGO works by having two long 4-kilometer tunnels arranged in an L shape. A laser beam is split and sent down each tunnel. The beams bounce off mirrors at the end and come back to a detector. Normally, the two beams cancel each other out perfectly, but if a gravitational wave passes by, it will stretch one arm of the L and squeeze the other by a tiny amount, less than the width of a proton. This puts the laser beams out of sync, and the detector sees a signal. The detection of gravitational waves was a monumental achievement. It was like hearing the universe for the first time after only ever being able to see it. It proved that space-time is not just a passive background, it is a dynamic, physical thing that can ripple and shake. So what does all this mean for us? It means our universe is a much stranger and more wonderful place than we thought. We live in a world where space can be warped and time can be slowed. We live on a planet that is not being pulled by the sun, but is instead rolling along a valley in a four-dimensional landscape. The very fabric of reality is not a rigid stage, it's an active participant in the story of the universe. It shapes the paths of planets and light, and it is shaped by them in return. Every bit of matter and energy leaves its mark on the geometry of the cosmos. And while we may not be building warp drives or opening wormholes anytime soon, we are part of this process. The simple fact of our existence, our mass, contributes to the overall shape of spacetime. We are not just living in the universe, we are part of its structure. Thinking about spacetime can be difficult. It challenges our most basic intuitions about the world, but it's a powerful idea. It shows us how interconnected everything is. The movement of galaxies, the ticking of a clock, the fall of an apple, the path of a beam of light, they are all governed by the same underlying principle, the shape of spacetime. It's the grand invisible architecture of our reality, and we've only just begun to understand it.